Okay, so at this point, we've talked about a number of different derivatives of different kind of functions. We've talked about additive, subtractive, chain rule, product rule, quotient rule. So we can do a lot of different things. But we are currently limited to functions that are um, a function of one variable, right? So like g of x, f of x, right? So a variable of x. And so we call these types of derivatives ordinary derivatives. And so the notation we use is a little d g or df divided by dx, right? So this is a traditional method that we've been using in this series. Now I'm going to make a short video because actually the concept is pretty straightforward, just one extra step. We changed the letter d to a script d or partial, and this is known as a partial derivative. So when you see a derivative written in this form, where it's not a traditional d, it's a script d, this means we're looking for the partial derivative. So what does that mean? That means this function f is no longer just a function of x like this function g is. It's a function of, it could be x, y, z, it could be r theta phi, r z theta, whatever it might be. It's a function of multiple variables. And so we need to specify that we're going to take the partial derivative. So we're going to only focus on that one variable for this setup. And all you have to really do is consider the other variables in this context as constants. So I'm going to go through an example, and it's just breaking down the problem, or you're breaking down your function into simpler, smaller components, and then taking the derivative of it. Kind of like what we did with the additive subtractive method. You just break it down to its fundamental pieces, and once you have this table, actually it's not very difficult to solve. So we're going to go through that in this quick video. All right, so let's take a look again just to remind ourselves how we take an ordinary derivative. Here we have an ordinary function, g of x. So that means g, the function g is just a function of x. So it's equal to 5x squared plus sine of x. So there's an additive term here, so we can use the additive properties of derivatives and just find the derivative of this term, and then separately find the derivative of this term. Since I'm looking for the ordinary derivative, I can focus on looking at dg dx, right? So regular d, so this is the ordinary derivative. And so I can take the derivative of 5x squared with respect to x. So I have a constant 5 times x squared. So I can break it up with this rule that we saw. So the constant times the derivative. So it's basically 5 times the derivative of x squared. So I'll go back here to my table. So I take 2, which is my n term, 2 times x to the 2 minus 1, or x derivative of x squared just becomes 2 times x. So it's 5 times 2 times x is 10x. And then separately I have sine x. So the derivative of sine x we see here is positive cosine x. So we have it there, right? So simple, you've done this before. This is your ordinary derivative. So let's just take a look at an example for a partial derivative. So I'm going to give us, we need a function that is a function of more than just x. So I just, came up with this function of x, y, and z. So we have terms that are just x, so 5x squared again. I have terms that both have y and x, so 3y cosine x. I have terms that have both z and y, z squared over 4y, and I have terms that are just z, ln z. So any combination actually still works. So what we're going to do is take the partial derivative of f with respect to x. Separately, we'll take it with respect to y, and then separately, we'll take it with respect to z. Now remember the notation. So when I take the partial derivative, instead of writing d, little d here for the derivative, we're going to use script d. So I use script d here, right? So ignore this for now. We'll break it down step by step. So script df dx. So this is with respect to x. So what does this tell me? This tells me I'm going to take the derivative of each of these terms, because I can still use the additive rule, I can still use product rule, I can still use quotient rule, chain rule, all of those still hold true. All right, so here we have 5x squared. So I'm going to take the partial of 5x squared with respect to x. partial of 3y cosine x with respect to x, the partial of z squared over 4y with respect to x, and the partial of ln z with respect to x. So the same exact setup that we did for this one using the additive derivative method. Now, what we do next is we consider anything that is not x to be a constant. So for this first term, it's the same thing, right? So that's just going to be 10x because it's all x terms. So that really doesn't make a difference. Here, we have a y term. So we're going to look at this y value as a constant, just like we look at 3. So essentially, it's going to be right here. Constant c here, in this case, is going to be 3y. So it's just going to be a constant times the derivative of cosine x. We go over to my table. Derivative of cosine x is negative sine x. So this will be negative 3y sine x. Over here, I have z squared over 4y. I have no x terms. So this whole thing is a constant. What's the derivative of a constant? Here, this tells me it's equal to 0. So this term will be equal to 0. Similarly, I have a natural log z term here, no x values. So this term will also go to 0. So I'll get 10x from this term. I get a negative 3y sine x from this term. This term gives me 0, and this term gives me 0. So we simplify this to 10x minus 3y sine x. And that's my partial of f of x. Give it a try. Pause the video and see if you can take the partial of this function with respect to y and z. And I'm going to finish up this video with those simple processes in the same exact setup, right? So if you're going to give it a try, I would suggest start by writing this form with respect to y instead of with respect to x, and then for the next problem with respect to z instead of with respect to x, and then break down each individual component. All right, so press pause if you want to give that a try on your own. If not, let's continue working through it. So we're going to next take partial of f with respect to y. So this is exactly the same thing as what we see here, but instead of with respect to x in each of these terms, we have it with respect to y in each of these terms. So now, instead of y and z being constant in this partial f partial x, when we look at partial f partial y, y is our only variable from our context. So x and z are considered constants. So for this first term, there are no y values. So this is just the derivative of a constant. So this will be 0. Over here, I have 3y cosine x. So 3 cosine x becomes my constant. So basically, it's 3 cosine x times the derivative of y with respect to y. Well, if I could look over, where is it? Right here, y to the nth power of 1 is just going to give me 1, right? So this will be 3 cosine x. Over here, I have z squared, which is a constant, over 4, which is a constant, divided by y. So what my 1 over y is my only variable. So that's basically the same thing as y to the negative 1th power. So I go over here, y to the negative 1, n is equal to negative 1. So this will be negative 1, y to the negative 1 minus 1, or y to the negative 2, or 1 over y squared term. Okay. Then this last one here, ln z, or natural log of z, I have no y values. So this will also go to 0. So let's walk through that again. This one has no y values, so that's 0. This one has 3 cosine x as my constant. Then the derivative of y, with which we saw from here, is just going to be 1. So 3 cosine x times 1, or 3 cosine x by itself. Over here, we have z squared over 4 as my constant. And then it's just the derivative of 1 over y, or y to the negative 1. We can use this to see that's negative 1 over y squared, or negative y to the negative 2, right? And then here we have no y terms. So this is just going to be derivative of a constant. So that's just going to be 0. And then if we simplify this, we get 3 cosine x minus z squared over 4y squared. Okay, so it looks complicated, but if you break it down term by term, actually it's not anything different than what we've done. All right, so now let's take a look at partial f partial z. So again, this is the same equation as we saw here, but now we're looking at it with respect to z. So we have z terms down here. Now we can just break down step by step. No z terms here, so this is going to be 0. No z terms here, so this will also be 0. We have z squared over 4y, so 1 over 4y becomes my constant. right here, right? So it's 1 over 4y times the derivative of my variable form, which is z squared. Derivative of z squared with respect to z is just going to be 2 times z from this again. So this form comes up over and over. Sine and cosine form show up over and over. Then the partial natural log z with respect to z, I go over here, natural log, right? And that's just going to be 1 over z. So let's go step by step again. 0, 0, because no z terms in either of the first two terms. Right here I get 1 over 4y times derivative of z squared, 2z. And then derivative of natural log z, which we saw was just 1 over z. So this simplifies to z over 2y plus 1 over z. So you can see that partial derivatives and ordinary derivatives, the only difference is the notation to make us aware that it's a partial versus a ordinary derivative. All the rules of ordinary derivatives that we've talked about apply here, as we saw. And then the main thing is when you take the partial of a certain function, we can we treat all the other variables, right? So in terms of partial x, then we treat y and z as constants here. Partial y here, we treat x and z as constants, and partial z, we treat x and y as constants. Remember that rule, then the setup and the process is exactly the same. So usually what I would recommend as you're starting out looking at these partial derivatives is write out your full function, then write out each, like when usually it's additive or subtractive components as you're working through it, break them up like we do here, and then just work each term. These are basically sub problems that you would need to solve. And if you do that, I think you're going to be just fine. In the next video, we're going to take a look at second derivatives. So these are your first derivatives. We repeat it, and so we'll see how that looks for ordinary derivatives. We also will see how that looks for partial derivatives.